Stanford University.
The goal tonight is not to tell you why the Higgs boson is the best thing since flush toilets. You've read all of that. Anybody who's here has probably read all of the hype, the excited, breathless superlatives that have hit the newspapers and so forth. The Higgs boson is going to explain the origin of the universe and this and that. I'm not going to do that. First of all, before I say it, the excitement and the enthusiasm is justified. It's not that it's not justified. It is justified. The history is fantastic. It's an unbelievable event and so forth. But that's not what my thing is. It's not what I do well. What I do well is explain how things work. My goal tonight is going to show you, insofar as I can, in 1 hour, which is tough, which is hard, and it may not work, but as well as I can, to explain to you the nuts and bolts of what Higgs physics is about. One of my closest friends, incidentally, is named Francois Englert. And Francois Englert would be appalled if he knew that I was standing here talking about the Higgs effect, since Francois Englert was the discoverer of it. So from time to time, I may call it the Braut-Englert-Higgs effect. But I also may slip and slide and just call it the Higgs effect, because I tend to forget like everybody else. All right. So, how it works. First of all, there's a lot of moving parts, a lot of pieces that I would have to explain to you first to really do it right. And I'm going to try to explain those pieces in little modules, shall we say. It's a highly quantum mechanical effect. It cannot really be understood without quantum mechanics. And so I would begin with a course in quantum mechanics. And let's say the course in quantum mechanics consists of just one thing. Things are quantized. Quantized means that they come in discrete integer quantities. The most famous example of this is angular momentum. Angular momentum, the rotational properties of the rotational momentum of an object are quantized, which means they come in discrete steps, and the discrete steps are 1 Planck unit, 1 unit of Planck's constant. We'll take that as all we really need to know about, for the most part, about quantum mechanics tonight. The next concept, which is an easier one, at least I think it's an easier one, it's a classical concept, is the idea of a field. A field is just a condition in space. It could be the electric field, it could be the magnetic field, it could be a gravitational field. Whatever you think of as being present in space, which characterizes the behavior of space at that instant and in that place in space and time. And so space can be filled with fields. Now, ordinarily, you imagine in empty space is the thing we call a vacuum. From a quantum mechanics point of view, the vacuum is just a state of lowest energy. Nothing there, no energy, other than what quantum mechanics requires there to be there. And so you ordinarily think that the fields that could inhabit space are zero in empty space. The electric field, the magnetic field, and so forth. But there's no important requirement of physics that says that that should be the case. Let's imagine a world filled with electric field. How could that electric field get there? Well, it might be there because there are capacitor plates infinitely far away. So far away we can't tell they're there. There we would have a world in which there was an electric field. It would just be there. Empty space would have an electric field. Now when you think about fields, we're beginning a little bit too early. Okay, you're going to wait. I'll do that. All right, so what I was saying to the audience, two things. The first was that quantum mechanics we're going to summarize by one simple statement, that things are quantized in quantum mechanics. Quantized means they come in discrete bits. The most important example is angular momentum. Not the most important, necessarily the most important example, but the most important example for me tonight will be angular momentum. And angular momentum has to do with rotating objects and so forth. Angular momentum in quantum mechanics, unlike classical mechanics, comes in discrete units. The unit is Planck's constant. You can't have a tenth of a unit of angular momentum. You can only have angular momentum 0, 1, 2, 3, minus 1, minus 2, minus 3. You can also have half integers, but we're not going to worry about that tonight. But no, you can't have angular momentum pi, only discrete integers. That's the first fact that I want you to remember. The other fact from quantum mechanics that we'll have to remember also is the uncertainty principle, but we'll come to it. Now, the other thing we spoke about was fields. Fields are things that can fill space: electric field, magnetic field, gravitational field, other kinds of fields that exist in physics. They are functions of space. They can vary from place to place. And they affect, for example, the way things move. An example would be an electric field affecting the way a charged particle moves. Now, the other thing I said was you can imagine a world in which, for all practical purposes, empty space is filled with a field. An example would be if I went out to Alpha Centauri at that end and, excuse me, I don't know what's out there. Excuse me. Yeah, whatever's out there. And place some capacitor plates. Big capacitor plate out there, big one out there. Make an electric field in between. They're so far apart that we can't see them. We would say that the world is a world that exists with a magnetic field. And we would say that charged particles move in peculiar ways, but that was just a fact of nature. Generally speaking, fields cost energy. The space without an electric field has zero energy. With an electric field, it has energy. And if we were to plot the energy of a field, a typical field, could be electric, could be a magnetic, could be something else, generally we imagine that the field energy as a function of the field, horizontally imagine the value of a field, vertically its energy, zero field right here, and we imagine exciting the field, causing it to vibrate by giving it a push at some region of space, and nearby the field will vibrate. Those vibrations are quanta of the field. They are particles. They are particles. The quanta of vibration of the field are particles. Now, you might have a situation where there is more than one field relevant. Let's call it phi and phi prime, or whatever you want to call it. Doesn't matter. Then instead of plotting the field as one-dimensional, we might plot it as two-dimensional. Now, this is not space. This is the value of some collection of fields. And then the energy would depend on both fields. Here's an example, an energy function which looks like that, which simply says that no matter how you displace the field, it costs energy. Now, imagine that this upside-down paraboloid here, or whatever it is, was nice and symmetric, nice and rotationally symmetric in the field space, exactly like the top of my hat here, which, as you can see, is symmetric. And so the field as a, oh yes, where's my little, that's it, right. The field as a function of position would most likely, if the energy is as low as possible, just sit at the bottom of the potential energy of the field. Just to lower the energy as much as possible. So we might think of the field at every point in space, a little ball which can be made to oscillate back and forth and do things, and those are just oscillations of the behavior of physics in a local region of space. As I said, they often correspond to quantum particles, those oscillations, but for the moment they're just oscillations. Now, one of the things we could do if we had a field whose values were like the position in the hat here would be to start it out displaced from the origin, let's say up to here, and then start it moving in a circle. Just in the same way you could take this ball, and if the hat was really nice and smooth and symmetric, give it a push and it would go around in a circle. That circular motion of the field is very, very similar in a way to angular momentum. It's not angular momentum in space, but it's a kind of angular momentum that exists in the field space. That angular momentum, like all angular momenta, are quantized. They come in integer multiples of Planck's constant. What do they correspond to? They correspond to something else that is also quantized in nature, the value, for example, of electric charge. So in modern physics, the way one thinks about the electric charge in a region is that in some region of space, a charged particle is viewed as an excitation of the field in which the field is made to spin around in the internal space of the field. Not in real space, but in the internal space of the field. That's one way, in fact, it's the main way that we think about charge, as a kind of rotation in an internal space. Okay, now what I want you to do is imagine taking the hat and turning it over. Imagine that the potential energy was not, turn it over this way, excuse me. This way is the way that the potential energy is minimum at the crown of the hat. But if the potential energy really looked like that, so that it was maximum at the top of the hat, then the top of the hat would not be a position of equilibrium. It would be a position of unstable equilibrium. It would look like this. Turning over the hat, the crown of the hat now, this is the way the real hat looks like this. And it doesn't, well, okay, let's make the, how's that? That look like a hat? Yeah. Looks like a hat. What kind of hat does it look like to you? Looks like a sombrero, right? Looks like a Mexican hat. Physicists call this kind of potential energy function a Mexican hat, believe it or not. It's called a Mexican hat. It turns back up. The top is unstable. If a ball was put at the top, it would roll down, and where would it go? It would go to the brim of the hat. If, for some reason, the potential energy of a field was like this, then the state of lowest energy would not be at zero field, it would be out here. Now that's kind of interesting. It would be a vacuum, a world, which had a field, just like having an electric field, except it's not an electric field, in which the value of the field at every point in space was not zero. You might notice it. How would you notice it? Well, you might notice it because it might affect other things, and indeed it does affect other things, as we will see. But there's now something interesting you can do that you couldn't do here. Over here, if you wanted to set this thing into rotation, you would have to displace the field a little bit, because it doesn't mean anything to rotate right at the center. If you wanted to set up a rotation, you displace the field and then give it a flick. So making a charged particle costs some energy. Here, you can imagine setting this thing into rotation with just a little flick that costs no energy. It costs no energy because you don't have to ride up the side of the hat. In other words, you could have a motion in which, Got it. You got it. You got it. You understand. Right? You got to have a motion in which that field slowly wound around the top of the potential. In fact, it could do it everywhere simultaneously, not in real space, but in this field space. That would correspond again to a charge. If rotation in this internal space corresponds to some kind of charge, but now the whole world, if the whole field was moving like that, would have a little bit of charge in it, a charge density, charge filling space, at essentially no cost of energy. That phenomenon is called a condensate. It's called spontaneous symmetry breaking, but it's also called a condensate in space of charge. Now, you might say, okay, look, I want to find the lowest energy that the vacuum can have, that empty space can have. My best bet is to make the field not move with time. Just like a ball at the bottom of the sombrero hat here, there's also kinetic energy of motion. Causing the field to move around in a circle like that would cost some energy. So you would say the true lowest energy state of the world should be with the field either here or here or here. It could be anywhere along the rim of the hat, but it should be standing still, right? The problem with no angular momentum or no charge. Empty space should not have charge. The problem with that is the uncertainty principle. Let me remind you what the uncertainty principle says. It says that if you have an object and you're interested in its position, x, in ordinary space now, and its momentum p, velocity if you like, the uncertainty principle says that the uncertainty in its position times the uncertainty in the momentum is greater than or equal to what? Planck's constant. You can't have something both standing still and having zero momentum. If it's you can't have something standing still, namely no momentum, and also localized at a point. Delta p times delta x is greater than h bar. Same thing here. If you know where the field is on this Mexican hat, if you know with great precision, then it follows from the uncertainty principle that it must have a very large uncertainty in how fast it's moving around here. Ah, that's interesting now. That would say that you can't have empty space with no charge in it. Can't have empty space with no charge in it because if you lay the field down at this point, you know where it is on the rim of the hat, and if you know where it is, there's a necessary uncertainty in the charge being like the angular momentum. All right, so where are we then? If this were the case for electric charge, for ordinary electric charge, we would say that the vacuum, empty space, not only is filled with charge in a certain sense, but a totally uncertain amount of charge. Totally uncertain, and this is a quantum effect, a totally uncertain amount of charge. There would be equal probability, let's take a little volume of space, there would be equal probability that the charge was 0, or that the charge was 1, or minus 1, or 2, or minus 2, 3, minus 3. Now this is truly odd. This is not something you should try to visualize, because you can't visualize an uncertain amount of charge. But nevertheless, that is what a region of space would look like. If you measured its charge, it could be anything from minus infinity to plus infinity. Okay, now I want you to imagine that you have an extra charged particle. An extra charged particle, and you throw it in. You don't know initially what the charge is, but what does that do? It displaces the charge by 1 unit. Let's suppose it was a positive charge. You've displaced the charge by 1 unit, and so if it was 0 to begin with, it's now 1. If it was 1 to begin with, it's now 2. If it was 2 to begin with, it's 3. If it was minus 1, it's 0, 1, minus 1, minus 2, and so forth. But that's exactly the same as what we started with. We started with something which had an uncertain amount of charge, equally likely for any value of charge. And what did we end up with after we threw the charge in? Exactly the same thing. What if we pluck the charge out of this thing? Same thing. So a condensate is a funny configuration of space where, with respect to whatever kind of charge we're talking about, it's so uncertain that you wouldn't even realize it if you put an extra one in or pulled one out. Now, the real world is not like that with respect to electric charge. We know if we have a charge in space. So it's not like that with respect to electric charge. However, there are materials that behave like this. Superconductors. Superconductors are exactly like this. So it's not unheard of. It's not a totally new thing to have a condensate of charge, where in a region the charge is completely uncertain. Okay, that was module number 1, if you like. Condensates, or what is sometimes called the spontaneous breaking of symmetry. Module number 2, the Standard Model. Now we come to particle physics, and I'll give you a short course in particle physics. First of all, particles have mass, and the mass can be anywhere from 0. We're talking about small particles now. We're not talking about railroad engines or stars. We're talking about small particles. We'll call them elementary particles. But there's also a maximum mass they can have. If they were bigger than that, they would form a black hole. If they were more massive than that. If a point particle was more massive than something, it would form a black hole, and it would be something different. So up to some maximum, and that maximum is called the Planck mass. It is not a very large mass. It's neither a very large mass nor a very small mass. It happens to be about 1/100,000th of a gram, a small dust mote. But that is the heaviest that an elementary particle can be without turning into a black hole. And if you ask now, where on this chart, from 0, this is called m Planck, up to the maximum, where are the ordinary particles, the electrons, the photons, the quarks? They are way, way down here. The largest mass of a known elementary particle is about 10 to the minus 17 of the Planck mass. Why are the particles so light? Well, one answer is, in order to detect massive particles, you have to have a lot of energy. In order to have a lot of energy, you need a big accelerator. We've only made accelerators up to some size. And so, for all we know, the rest of this is filled with particles, and that's probably true. That's probably true, but what is special about these particles? Well, first of all, let me name them, and then I'll tell you what's special about them that makes them clump up at 0 mass. Let's name them the particles of the Standard Model. They come in 2 varieties. It is not important that you know the difference. Well, I'll give you a rough idea of what the difference is. They come in 2 varieties called fermions and bosons. The fermions are all the particles that make up matter in the usual sense. The electron, which I'll just call E. Well, the neutrino goes along with the electron. So that's a nu. The electron, the neutrino. Quarks. There's a variety of different quarks. Incidentally, there are several different kinds of electrons. We call them electron, muon, tau, it doesn't matter, but they're very electron-like, and several kinds of neutrinos. The electrons have the electric charge, the neutrinos don't. And then there are quarks, a variety of different kinds of quarks, up quarks, down quarks, this kind of quark, that kind of quark. And those quarks, several different kinds of quarks, you know what the role of them are. They make up the proton. And that's about it for fermions. For bosons, on the other hand, is first of all the photon, gamma for a gamma ray. Photon. There's an object called the gluon, G. It's very much like a photon. It's very much like a photon, but it doesn't have anything to do with atoms. It has to do with nuclei and protons and neutrons. It plays the same role in holding the nucleus, or better yet, the proton together, as the photon plays in creating electrical fields inside an atom. So there's the gluon. And then there are two others called W bosons and Z bosons. For the most part, we won't be interested in any of them except the photon here and there, but mostly we'll be interested in the Z boson. That's it. That's the standard model. That's all there is to it, with one exception. I've left something out. It's the thing you came to find out about tonight. Okay? So we'll come to it. If there was no Higgs boson, then this would be it. Now, what is special about this set of particles? What's special about them is, for reasons that I'm going to come to, reasons that I will come to, all of these particles in the standard model, as I've laid it out here, with nothing else in it, would all have mass equal to 0. They would be massless. And I'll explain why that is in a little while. We often hear that it's the role of the Higgs boson to create mass for particles, or to give the particles their mass. That's the expression that I've heard over and over. The Higgs gives particles. Why do the particles have to be given mass? Why can't they have mass of their own? Why do they have to be given mass? Well, as it turns out, for reasons we'll explain, this set of particles is exactly the set of particles which would have no mass if this was all there was. Now, in part, that explains, in part it explains why these particles are so very light. It's because they're massless. They have no mass. Well, not quite. We can't live with that because we know that particles really do have mass. Next question. I'm going to draw some figures over here. What do these particles do? What kind of processes are they involved in? All right, the basic process of the standard model, this is an oversimplification, but it's qualitatively right, is that the fermions, there's a fermion moving along, and I will describe a fermion by a solid line. Solid because it's what makes up stuff. Solid line that's moving from one point in space-time to another point of space-time. What the standard model does is it causes the emission of bosons. An electron moving along can emit a photon. Electron moving along can emit a photon, and that's connected with the electric charge. Any electrically charged particle can emit a photon. A photon. That's the first thing that the standard model does. Now, this, of course, is just quantum electrodynamics. It does not have to be the electron. It could be any electrically charged particle. Next, the quark. Let's see, do we have room here? Yeah, we'll just do it. The quark, let's just call it Q. The quark can emit a gluon. Precisely the same pattern. The quark emits a gluon. Now, the quark can also emit a photon if it happens to be electrically charged, then quarks are electrically charged, but electrons cannot emit gluons. Gluons are the things that bind quarks together to hold them together into protons and neutrons. And then there's one more important process for me tonight. There are two more processes, but I'll just write down one here. And it is either an electron, oh, incidentally, a neutrino cannot emit a photon. It has no electric charge. It cannot emit a gluon. It's not a quark. Okay? Both electrons and neutrinos, and quarks for that matter, can emit the Z boson. Where's the Z boson? Here's the Z boson right here. And when they do so, the Z boson being electrically neutral, the electric charge of whatever's here doesn't change. So this is another process that the standard model describes. Now, first of all, why are the bosons massless? Well, the photon is massless. We know that it travels with the speed of light. Now, could we make a theory in which the photon had some mass? Yes, we could. But the more important thing is that we can make a theory in which the photon doesn't have a mass. Why? Because the photon doesn't have a mass. Using the same kind of theory, the Z boson would not have a mass, and the gluon would not have a mass. Everything would be massless. These would be the processes that could happen. These would be the particles. They would all be massless. Okay, now, how do fields give particles mass? Or better yet, more simply, a simple example. I'm going to show you a simple example now. The simple example is how a field can affect the mass of a particle. We'll come back in a moment to how it can give something which didn't have mass, but let's take a more modest question. How may fields affect the mass? Or better yet, how might they make different masses for different particles? So I'm going to show you an example. This example is a little bit contrived, but it's a real example. A water molecule. Water molecules have the basic property that they're little dumbbells. They have a plus end and a minus end, electrically charged plus end and minus end. They're actually not, they're more like Y's, Y with 3 ends. But we can think of them as having a plus end, dumbbells, and a minus end. Now, the mass of a water molecules have mass. The mass of a water molecule doesn't depend on its orientation. If we turned it over and made a water molecule with its minus end here and the plus end here, it would have exactly the same mass. Why? It's the symmetry of space. Space is the same in every direction, and so by symmetry, we would say that the water molecule standing up straight has exactly the same mass as the water molecule standing on its head. Let's not worry for tonight about whether it's lying on its side. Quantum mechanics tells us we don't have to worry about anything but standing up straight and lying on its head. All right, so that's true about water molecules. Their mass is the same if they're standing up straight. And think of water molecules now as particles. Think of them just as particles. We don't know what they are. They're just little elementary particles. We can't see them. And so we have two kinds of particles, the upstanding and the standing on its head particle with exactly the same mass. Now, I thought I had a purple. No purple. I told them to put purple. We'll have to use orange. Where? Way over here? Underneath the board. You mean under here? Oh! Good. All right. I have my color coding in my notes here, and if I blow it, it'll be terrible. Okay. So, it looks brown to me. It is brown. Okay. Let's create a region in which there's an electric field. We're going to make a field. It could be between two capacitor plates. The capacitor plates could be far apart. It doesn't matter, but let's put them in the capacitor plates here and here. And inside that region, let's create an electric field. The electric field, in this case, pointing up. That means it pushes plus charges up and minus charges down, if I have my signs right. And let's take one of these water molecules and insert it in here. Once I insert the water molecule in here, the energy of the upstanding water molecule and the upside down water molecule are different. Which one has less energy? The one with the plus up has less energy, and the one turned over has larger energy. The water molecule itself is electrically neutral. It has no electric charge, but it's a little dipole. It has a pair of charges, and which one has more energy depends on the sign of the electric field. Okay, so there we are. We have two water molecules, two types of water molecules, two different particles. We could give them different names. We could call it water and scotch. And the water molecule has one energy. The scotch molecule has another energy. And there they are. Well, by E equals mc squared, this also tells us that the two molecules have different mass. Now, in practice, this would be a tiny different mass between them, but they would have different mass. So the same effect of this field, which exerts itself on charged particles, does something to neutral water molecules. Incidentally, notice that it doesn't exert any net force on the water molecule. The water molecule moves smoothly through it with no force, no net force acting on it. But there is a difference in the two configurations of the water molecule. And so it's as if we had particles of two different mass. So this is just an example of how a field creates mass. In this case, it increases one mass and decreases the other mass. Incidentally, if you read some of the literature, and they'll tell you about how the Higgs field gives a mass, I've read any number of places that it's something like space being filled with molasses. It is not like space being filled with molasses. The vacuum is not sticky. And one of the things that molasses would do, well, the idea is that massive particles move slower than massless particles. So the idea is that molasses slows them down. But fields don't slow particles down. If you give the particle a push in this direction, it will just continue to move because there's no net force on it. It'll just slide right through this thing, frictionlessly, no impedance, no friction, no molasses. There's not, the other analogy I once heard is that it was like trying to push a snowplow through a heavy snow in the Arctic. It's got nothing to do with it, whatever. That's a lazy way to explain it, and it's a wrong way to explain it. Okay, so there we are, but now let's think of this in a slightly different way. The electric field in here can also be pictured in terms of photons. A field is another way of talking about a collection, a condensate of photons, an electric field. We can replace the electric field by a condensate, the same kind of condensate of photons. Let's draw photons by just little squiggly lines. Fill this up with photons. How does it know which way the electric field is pointing? Well, photons have a polarization. They could be up or they could be down. So just imagine this thing being filled with photons, but not filled in the usual way, but filled in a condensate. What does a condensate mean? A condensate means that if I pull one out, it doesn't make any difference. If I put an extra one in, it doesn't make any difference. That's the meaning of the condensate. So it's an indefinite number of photons. That's what a field is, indefinite, and if you pull one out, nothing happens. And now let's reintroduce the water molecule. Let's just draw the water molecule moving through here. Now I'm going to make the water molecule red. I've already blown my color coding. Here's a water molecule moving through here. And what is it going to do? It has charged particles inside it. The charged particles can emit and absorb photons. They emit and absorb photons. We've made the photons green now. So it emits photons, but when it emits a photon, putting an extra photon in doesn't matter. And so we usually draw that by just putting a cross at the end. A cross simply means that throwing an extra photon in doesn't affect anything. Photon is emitted and just is absorbed, or is just disappears into the condensate. Okay. As this object, the dumbbell, moves through the electric field, it's constantly emitting and absorbing these photons, which get lost in the condensate. That is another way of talking about how the field affects the particle. And depending on whether the photons are polarized up or down, this effect of constantly absorbing and emitting photons will have the effect of shifting the energy of the two configurations of the dumbbell. That's simply an example of how a field can affect the mass of a particle and how it can be thought of in terms of particles and condensates. That's what I want you to keep in mind, that picture. Okay, now let's come to elementary particles, not dumbbells, not molecules. First question, is there any reason why a particle or an object just can't have a mass? Does it need an excuse to have a mass? Does it need anything called the Higgs phenomena to have a mass? Well, there are lots of things in nature that have mass and have nothing whatever to do with the Higgs phenomena. Let me give you an example. Imagine you had a box, and let's make that box out of extremely light stuff, the lightest stuff you can think of, but it's a box with good reflecting walls, and fill it with lots of high energy radiation, bouncing off the walls but never getting out. It's made out of massless stuff. The photons are massless, they have no mass. The box we're imagining is made out of stuff which is exceedingly light, doesn't have much mass. But there's plenty of energy in there, lots and lots of energy. Well, E equals mc squared. And so this box will behave exactly as if it had a mass. We didn't need anything to give mass, just energy. That's all it took. Are there any particles which are like this, which get mass having nothing to do with Higgs or anything else? Yes. The proton. The proton is a particle which is made out of quarks. Quarks, 3 quarks, and a bunch of gluons, G's. A bunch of gluons, a large number of gluons. Quarks and gluons in the Standard Model are massless. Does that mean that the proton would be massless if the quarks and gluons were massless? Not at all. If the quarks and gluons were massless, the effect on the proton would be about a 1% or even less change in its mass. Not much at all. Where does its mass come from? It comes from the kinetic energy of these massless particles rattling around in a box. The box being created by the proton. So mass doesn't have to come from black holes are another example. Black holes have mass. It doesn't come from the Higgs phenomenon. It doesn't have anything to do with Higgs. So what is it about the models of the particles of the Standard Model which require us to introduce a new ingredient? So I'm going to concentrate on the electron. Let's concentrate on the electron. We don't need all of this. And what I need to tell you about is the Dirac theory of electrons. But really, we don't have to know very much about the Dirac theory. All we have to know is that electrons have spin. And furthermore, if an electron was moving very fast down the axis here, let's say with close to the speed of light, we really accelerate that electron, then there's 2 possibilities. The spin of the electron can be right-handed, like that. Think of my thumb as the direction of motion of the electron. It can be going that way, like my right hand, or it can be going that way, like my left hand. Ooh, I didn't even realize I could do that. Now, 2 kinds of electrons, right-handed and left-handed. Okay. Now, do right-handed electrons always stay right-handed? Can they flip and become left-handed? Can the right-handed become a left-handed and left-handed become a right-handed? Yeah, that's exactly what the Dirac theory says. But if it was moving with the speed of light, it couldn't. Why not? Because if a thing is moving with the speed of light, time is infinitely slowed down and nothing can happen to the object. It just moves along, but nothing can happen internally to the object. So if its mass was 0, it couldn't flip. But in the Dirac theory, this flipping back and forth between, I tend to do it this way, but that's not right. This way, this way, this way, this way. That is intimately associated with the mass of a particle. And in fact, the mass of a Dirac particle is simply proportional to the rate at which it flips from left to right. That's the Dirac theory in a nutshell. Mass is the rate for the electron to flip back and forth from left to right. Okay? Of course, the faster it's going, the slower it will flip, but that's all right. You take that into account. So mass is left to right to left to right. And we could draw the motion of an electron in the following way. Here's the electron moving down the axis. At first, it's right-handed, so it's going this way, and then it's left-handed, it's going this way. And then it's right-handed. Can you tell the difference? Maybe not, but that's okay. And in between, it jumps from one to the other. The probability or the rate at which it jumps is a measure of the mass of the electron. So it jumps back and forth and back and forth. Now I'm going to ask you to believe something really crazy. Do you remember the Z boson? Where's the Z boson? The Z boson was associated, was emitted. It could be emitted from electrons. It could be emitted from neutrinos. But let's concentrate on electrons. It is not the same as the photon. And the thing which emits it is not the same as the electric charge. It is another kind of charge, a completely separate kind of charge. It's like charge, but it emits Z bosons. We need a name for it. We don't have a name for it. Well, we do have a name for it. It's a very awkward name. It's called the weak hypercharge. I don't like that. Because it's the thing which emits the Z bosons, I call it zilch. Zilch. Zilch is like electric charge, but it's not electric charge. When a particle which has zilch accelerates, it emits a Z boson. It may also emit a photon if it also happens to have electric charge. Now, electrons, both right-handed and left-handed, have the same electric charge. Okay? But left-handed and right-handed electrons do not have the same zilch. In the Standard Model, this is part of the mathematics of the Standard Model, the left-handed and the right-handed electrons have different zilch. The left-handed electron has zilch of +1, and the right-handed electron has 0 zilch. I didn't make this up. In fact, my friend Steve Weinberg didn't make it up. If anybody made it up, he's up there or down there. I don't know where, but it is just the way it is. It is the way the mathematics of the Standard Model works, that the left-handed and the right-handed particles have different zilch. And now we have a puzzle. When the electron moves along and it flips from left to right, that means the zilch goes from +1 to 0. But zilch is like electric charge. It's conserved. How can the zilch go from 0 to 1? It can't. It can't. And that's the reason that the electron in the Standard Model doesn't have a mass. Because the left-handed and the right-handed have different value of a conserved quantity. And so left can't go to right. Period. No mass. Okay? How do we get around this? We get around this by introducing a new ingredient, and the new ingredient is called the Higgs boson. It's not the Higgs boson, not yet. We haven't gotten to the Higgs boson yet. We've gotten to the Higgs boson. The Higgs boson is one new ingredient. It is closely connected with this Mexican hat type configuration here. It's a kind of particle, but it forms a condensate. You can't tell how many are there. You can put one in, you can take one out, and so forth, without changing the vacuum. So we have one more ingredient. It's a condensate that space is filled with. And the nature of the condensate is it doesn't have electric charge. It has zilch. And it's a condensate, meaning that if you put a zilch in, nothing happens. If you take one out, nothing happens. And let's ask now what that means. The left-handed electron coming in has a zilch of 1. Let's call it a Z of 1. The right-handed has Z equals 0. Back to the left-handed, Z equals 1. Is that possible? Only if you emit something at this point which carries off that Z equals 1. A Higgs. The Higgs boson gets emitted. It carries a Z equals 1. But what happens to it? Where does it go? It goes into the condensate. It gets lost in the condensate. You put one in, and it just gets absorbed into the condensate. And so the electron goes on its merry way. The condensate absorbs the zilch, and it goes from 1 to 0. But then it can borrow a particle back from the condensate. Borrow one back, it doesn't even have to borrow it. If you pull one out, nothing changes again. And so it goes on its merry way from left-handed to right-handed, from left-handed to right-handed. Every time it switches, it emits a particle carrying this zilch quantum number, which then just gets absorbed into the condensate. That's the mechanism by which a field, and in this case, it's a field which forms a condensate by itself. It doesn't require capacitor plates. It just requires the energy to be such that the field naturally gets shifted. And that's the mechanism by which electrons, quarks, and the various partners of those particles, the mu particle, the tau lepton, all those ordinary and extraordinary particles, the fermions, get their mass by this phenomenon here. Phenomenon doesn't really have a name. It's called the spontaneous breaking of chiral symmetry, but it does have a name. But this is what it is. Okay. What about the Z boson? I told you before the Z boson is like a photon. Photons are massless. How does the Z boson get a mass? So I'll just show you something very similar happens to the Z boson. Let's remind ourselves what a Z boson can do. It can take any particle which has a zilch, and in particular, this green Higgs particle. It can take the Higgs particle, and the Higgs particle can emit a Z boson. It has charge, not real charge, but zilch, and zilch emits Z bosons. All right, so now let's ask what that means. That means that a Z boson moving along can do something a little bit similar to this. It can absorb some zilch out of the condensate, but now it has zilch. Originally, it was just a Z boson. Z bosons don't have zilch. It absorbs some zilch, and it becomes a Higgs. The Z boson becomes a Higgs, but then it can emit the Higgs, which gets lost in the condensate again. And the Z boson just moves on its merry way, constantly going back and forth from being a Z boson to being one of these imaginary, not imaginary, Higgs particles. That's the nature of the way that particles get mass from fields. This phenomenon of the Z boson getting a mass is called the Braut-Englert-Higgs phenomenon. This is the one that's called the Higgs phenomenon, the Z boson getting a mass. Now, this could have happened to the photon. Had there been a condensate of ordinary charged particles, the photon would have become massive. We would all be dead if that were the case. Massive photons would not be healthy for us. And so we are very lucky that, that this phenomenon here did not apply to ordinary electric charge. Will we ever discover the Higgs particle? Sure, we discovered it long ago. It's just part of the Z boson. The Z boson was discovered, it was postulated in 1967, or even before that by many people. But it was discovered, I don't even remember, around 1980. I forgot when the experiment at SLAC first discovered the existence experimentally. But when it was discovered that there was a Z boson, that it had a mass, and that when its properties were studied, the properties were not only consistent, but required that it was a thing which went back and forth and back and forth and back and forth between pure Z boson and the Higgs particle. So they've existed. We're not in doubt about them, and we never were, at least not for many years. So far, I have not mentioned the Higgs boson. So what is the Higgs boson? Well, the Higgs boson has to do with this condensate. It has to do with this condensate, but it's a different kind of excitation than sliding around the edge of the sombrero here. It does not have to move. It's not something which has to do with sliding around here. It has to do, I'll tell you two different ways to think about it. You have a condensate, and you can imagine the condensate has a density of these fictitious particles in the condensate. Imagine something which changes the density of them, kind of like a sound wave, a compression wave of some kind, which squeezes them closer and closer apart, makes them more and more less dense. That kind of vibration is what a Higgs boson is. Another way to think about it is that it doesn't have to do with sliding around the periphery of the sombrero. You go to a place in space and start the field oscillating this way, in and out this way. The further away it is, the stronger the condensate. The closer to the center, the weaker the condensate. So when it sloshes back and forth, it's kind of a compressional wave in the condensate. That mode, that phenomena, that oscillation is what is called a Higgs boson. The Higgs boson is like the sound wave propagating through the condensate. The reason it has been so important is because it was the one element that had not yet been discovered. As I said, the Higgs was discovered long ago. The Z and the W, the electrons, and all the others were discovered long ago. And so the next question, which I'll try to answer in 5 minutes, is why it was so hard to discover the Higgs, what we discovered about it, and very, very quickly what the future might or might not bring. Try to do this in a couple of minutes. Okay, so what kind of thing does the Higgs boson itself do? Now we're talking about the Higgs boson, not the Higgs boson, not the Z boson, the Higgs itself, the one that's been so elusive all these years. It's called H, and what it can do with some probability is, for example, create, we read this from left to right, a Higgs boson moving along in time is now to the left, can create an electron and a positron. It can create a pair of quarks. It can also create other things, a mu particle, or a top quark, or a bottom quark. All of the different quarks, electrons, also neutrinos, all the various fermions can be created in pairs when a Higgs boson decays. You say, if it's like a sound wave, why does it decay? Well, believe me, sound waves decay. If they didn't decay, you'd continue to hear my voice ring forever and ever, wouldn't you? So sound waves do decay. And it is possible to think of sound waves as decaying by creating particles. So the Higgs boson decays. It decays quickly if it exists, if it really exists. It decays quickly either into an electron-positron or a pair of quarks, or maybe some other of the fermions that exist in nature. You can read this diagram in two different ways. Oh, incidentally, the probability that the Higgs decays like this is proportional to the mass of the particle that it decays into. The heavier the mass, the more strongly that particle is coupled to the Higgs boson. So heavy particles are favored and light particles are not favored. Now you can read this diagram in either direction. You can say the Higgs boson decays, but you can also say an electron and a positron confuse together to make a Higgs boson. Well, if we want to make Higgs bosons and see them in the laboratory, we want to read the diagram from right to left, and we want to say this is a process whereby a pair of electrons can come together and make a Higgs boson. We've been colliding electrons and positrons for a long, long time. Almost as long as I've been a physicist, not quite. We've been colliding electrons and positrons together, and nobody was ever able to discover the Higgs. Now, one reason in the early days is it turns out that the Higgs is a fairly heavy particle. I will tell you what its mass is, but it's a fairly heavy particle, and unless you have enough energy, you don't have enough energy to make the Higgs boson. But there's a more important reason. In fact, SLAC, in the later days of SLAC's life, had plenty of energy to make the Higgs. The problem was the weakness of the coupling. The smallness of the mass of the electron translated into a very weak, improbable cross-section. Too small an effect, too unlikely to make the Higgs. And so when you collide electrons together at high energy, electrons are just not favorable. They're too light, and because they're light, they tend to not make Higgs with any appreciable probability. Well, how about quarks? We can collide quarks together. The usual quarks that make up the proton and neutron are also very light. And because they are light, also unlikely to ever make a Higgs boson. Well, I'm sure they were made in SLAC, but never in appreciable numbers that it was possible to detect them. So that was the main difficulty. The lightness of these particles was the thing that essentially prohibited us from making Higgses in abundance at SLAC or in other laboratories where collisions took place. What is the most favorable particle, most likely particle for the Higgs to decay in? The heaviest. The heaviest of the fermions, and the heaviest of the fermions is called the top quark. The top quark is hundreds and hundreds, thousands of times heavier than the electron, many times heavier, many thousands of times heavier than the electron. And the Higgs preferentially will decay into top quarks. So we'll just call those the quarks. They are quarks, but they're very heavy. 170 times the mass of a proton, basically, which is heavy. Top and anti-top. Top quarks and anti-quarks. So you say, well, look, now it's easy to make the Higgs boson. You just, it's actually, in fact, not possible for the Higgs to decay to two top quarks because the two top quarks are too heavy. But if you read it the other way and you take a pair of top quarks and collide them together, you can make a Higgs. So it's easy. We just go in the laboratory, take a pair of top quarks, collide them together, and make a Higgs. Well, the problem is that it's not so easy to find top quarks in nature. Why not? They decay very rapidly to the other quarks. They're not sitting around. You can't put them into the accelerator and accelerate them. They disappear in a tiny fraction of a second. There are no top quarks sitting around. Not even buried inside protons and so forth, not even buried inside other kinds of particles. There are no top quarks around. So we have to make the top quarks somehow in the collision. How do you make a top quark? All right, so here's a way to make a top quark. A gluon can come along. This is a gluon now. And remember what gluons do. They couple to quarks. One possibility is that the gluon can make a top quark and an anti-top quark. Well, there's plenty of gluons around, as we'll see in a moment. So why don't we just take a gluon and make a top quark and an anti-top quark out of it? The reason is because gluons are very light. They're almost massless. They don't weigh very much. Top quarks are very heavy. There's simply not enough energy in the gluon to create a pair of top quarks. So what we have to do is we have to take a pair of gluons. Now here's a process that you can imagine. Take a pair of gluons with a lot of energy, moving toward each other with a huge speed, plenty of energy, let one of them make a pair of top quarks for a short period of time, and then let the other one come and be absorbed by one of the top quarks. There we have it, a pair of top quarks created by a pair of gluons, a pair of high-energy gluons smashed together and make a pair of top quarks. Once we've created those pair of top quarks, the top quarks can come together and make our Higgs boson. This is the way we usually draw this, is to just draw gluon, gluon, and then a triangle, Higgs. These are top quarks going around the loop here. That's the most efficient process for making Higgs bosons. But where do you get gluons from? Gluons aren't floating around. Well, yes, they are. The proton is filled with gluons. The proton, mass of the proton is maybe 50% energy from gluons or something like that. It's filled with gluons and quarks. You take two protons and you collide them together, and the gluons inside the protons can collide during the collision and do this. That was what was detected at LHC. LHC is a proton-proton collider. It collides protons together, and when protons, a very indirect way, two protons collide together, a gluon from each one of them scatter, collide, create a pair of top quarks, and then the top quarks then have plenty of come together and create the Higgs boson. That's the process that was discovered at LHC. And it took a long time to get there. It was a hard thing to do. It was a very, very hard thing to do. But now it's done. We know the mass of the Higgs boson. It's 125 GeV, about 127 times the mass of the proton. And that's, I think, a finished fact. Before I quit, let's talk about the near future. What have we learned? We've learned that the Standard Model is essentially correct. We've learned the Standard Model is essentially correct. Everything seems to fit together. The Higgs boson fitting together. Remember, it's not the Higgs boson really that gives the particles their mass. It's the Higgs boson. But the Higgs boson is just what's left over when you think of these density oscillations. It was the last remaining piece. It is now in place. It's finished, but is everything fitting together exactly right, quantitatively right? Well, that we don't know. We don't know. There's one hint of a discrepancy, and I'll tell you what the hint of that discrepancy is. Let's, I drew this picture. Let me draw it again over here. It's the process of creating a Higgs by two gluons coming together. Gluon, gluon, top quark going around the loop, and Higgs. Now, this same process, once the Higgs is created, also allows the Higgs to decay. But it's not so easy to see gluons in the laboratory. They're difficult to work with. That's not the best process for looking for the Higgs boson after you've created it. The best process is to replace the gluons by photons. I don't have to even change the picture. Photons. It's exactly the same process, except with photons out here. Once the Higgs is created, by whatever it can create it, it can decay into two photons. It's an intricate process. It involves a lot of theory and a lot of calculation, a Feynman diagram. Not easy to calculate, but you can calculate it. And it depends on the properties of the top quark going around here. At the moment, and I'm not an expert at this, I can only quote what I'm told. At the moment, the Higgs boson that was produced in the laboratory appears to decay into two photons a little too quickly, about 1.5 times too quickly. Now, everybody agrees that that is not a statistically really significant fact yet. But what will it mean if it persists? It doesn't seem like a big deal, 1.5 times too fast. But the point is, the theorists have the ability to calculate that rate very accurately. A 1.5 times too big a rate is serious. It means something is going on. The most likely thing that would be going on is that there's another kind of particle in addition to the top quark that has not been discovered yet that can also participate in the same kind of, it's called a triangle diagram. Some other kind of particle. That, of course, would be big news. If there's something there that is not described by the standard model, that would be big news. It could be a supersymmetric particle. It could be anything, all kinds of things. If this is something to watch for now. The buzzwords are the decay of the Higgs into a pair of photons and a excess of about 1.5. I think it's a 2 sigma effect, whatever that means. It means something to statisticians. It means that it's not so robust, but it could be right. Right? If it turns out to be right, it means that we've discovered something unexpected. Or it might be even something that's expected, but something new beyond the standard model. Remember, the standard model is over 50 years old, well over 50 years old. And so 1967, am I right? 77, 87, 97, 2007. No, not quite, getting on 50 years old. So discovering the Higgs boson wasn't really discovering anything, it was confirming something. If this should be off by a factor of 1.5, one will have discovered something absolutely new. So if you want to watch, if you want to be a spectator in this sport, and you want to watch what happens, this is the thing to watch for next, whether the Higgs decays are consistent with the standard model. Okay, that's, we're finished. Thank you very much, and I hope you all got something out of that. One or two questions? Yeah.
What would cause two different fermions to have different rates of chiral oscillation?
Good. The answer is going to be an unsatisfying one. The answer is that the fermions have what would cause different fermions to have different masses? Different masses, essentially. Yeah. Different oscillations, different rates of oscillation are the same as different masses. The coupling strength, the coupling constant that couples the relevant particle to the Higgs field. Remember what happens? The particle moves. Yes, each one has a separate coupling constant, emits this, what did I call it? The zigs, emits the zigs which gets lost. There's a coefficient here, which is basically a probability. Each one, and we don't know why they are what they are. We know how to parameterize it, but we don't know how to explain it. For each kind of particle, let's say the electron, or the mu particle, or whatever it happens to be, there's a different constant there, and that constant is the constant which determines the rate and the mass. It's the same constant which comes into telling you how rapidly the Higgs decays into these particles, and therefore the heavier the particle, the stronger the decay. So that's a good question. I meant to say something about it and I forgot. Good.
Do we know the value of the Higgs mass? Do we know the value of the vacuum expectation value of the Higgs field?
Mm-hmm. Yeah, we've known that for a long time. 240 GeV. The value of the expectation value is, from one language, it's simply the displacement of the field. In another language, it's the density of the condensate. You can think of it either way, the density of the condensate or as the value of the displacement of the field. And that's why oscillation in the magnitude of the field is the same as a density fluctuation.
Does that give the vacuum an energy density?
What's that?
Does that give the vacuum an energy density?
Apparently not. Apparently not. Well, yes, I think it does, but there are many, many other things that give it an energy density, and for whatever reason, they almost all cancel out. This is one of the great mysteries of, right. So that's a very good question to which we don't have an answer at the moment. Right. Okay, I hope you got something out of that. I had fun preparing it and figuring out how to try to explain it. For some of you, you probably got something. Others are just mystified and sitting, what are they talking about? But that's it.
For more, please visit us at stanford.edu.